Welcome to Module 4, Lesson 3, where we are going to talk about scatter plots and lines of fit. These are the standards we'll be going over today. We have seen these two in the last two lessons. Today we're going to continue to write a linear two-variable equations to represent relationships. And we are going to start off with doing this standard today as well. And it states that fit a linear function to bivariant number data that suggests a linear association and interpret the slope and y-intercept of the model. Use the model to solve real-world problems in terms of the context of the data. So we are going to draw scatter plots, draw a best fit line, and write an equation for that best fit line to help us model real world problems in terms of the context of the data today. And the objective is that students use scatter plots and lines of fit to make and evaluate predictions. So let's define scatter plots. Bivariant data consists of pairs of values. Bivariant two variables. So right on the side of your paper, I want you to write bivariant. And right under it, I want you to write two variables. And again, my two variables would be x and y. So it consists of a pair of values. That is what bivariant data is. And using the bivariant data, we can create a scatter plot. And it is a graph of bivariant data that consists of ordered pairs on a coordinate plane. Scatter plot is exactly what the name says. It's a scatter plot. Plots, which is my points, are all over the place. They're scattered. Using a scatter plot can help you see the trend or general pattern in the data. Trends can be used to determine association in the data. Association describes the form, direction, or strength of the relationship between the two variables in a bivariant data. Descriptions of association includes linear or nonlinear, positive or negative, and strong or weak. The direction and strength of linear association can be measured by positive or negative correlation. So when we talk about association, since we know that we are not dealing with linear relationships, just because we have x and y does not mean we have linear relationships. What we're dealing with is bivariant data that has some type of relationship with each other, and we can use these terms to describe the association. What we are going to start off with is positive or negative correlation. In negative correlation, we talk about how the graph looks, the direction. So as you can see, these dots are moving upward. So as x increases, y increases, and we say this is a positive correlation. As you can see, these dots are moving downward. So as x increase, y decrease. So this is a negative correlation. And as you can see, my points are all over the place. X and y are not associated, so we have no correlation. You can also see this graph increases from left to right, and this graph is decreasing from left to right. So that's why we have a positive and negative correlation. When we do our scatter plots, we sometimes have our points being gathered in one spot. We call that a cluster of points. And sometimes you have some points that does not go with the trend of your data. And we call that an outlier. So think about it. When you have a clique and you all are hanging out together, we call you a cluster. But when you have that one person that sits on the side and not eat lunch with nobody and eat by themselves, that is the outlier. So let's do some examples. The scatter plot displays the height and weight of New Orleans Saint football players. Determine whether the scatter plot shows a positive, negative, or no correlation. If the correlation is positive or negative, describe its meaning in the situation. So as you can see, my dots are moving upward at a trend. It's not steady, but as you can see, they are moving up as a trend. So I can say the scatter plot shows a positive correlation. As the height of the football players increases, weight usually increases as well. And this is what we called a cluster. So as you can see, my dots are clustered up in one group. Now I want you to do the check. The scatter plot displays the number of landline telephones in the United States in 100 million since 2000. Determine whether the graph plot shows a positive, negative, or no correlation. Describe the correlation meaning in the situation. So you should have told me that it was a negative correlation. As time increases, because that is what's on my x-axis, the number of landlines generally decreases. So again, it is not constant, so that's why we're not saying constantly decrease. It is generally decreasing. Also, when we are talking about correlation, what you need to remember is that not all points need to follow the trend. Majority of the points need to follow the trend. So as you can see, yes, it is decreasing, but as you can see, this point increased in this 1 year. But we can still say that it has a negative correlation because majority of all the points are going down. So not all points have to follow the trend, but majority needs to for us to have a correlation. Now let's talk about the line of fit. A line of fit is used to describe the trend of the data in a scatter plot. The line of fit is a linear function, so it is a straight line that we draw through the data. No, we do not draw it through every single point because as you can see, scatter points do not make a straight line. But you need to draw it so that it represents the trend of the data. So to do that, you first need to make a scatter plot. You have to put your points on a graph. Once you do that, you draw a line. Like I said, not all the points need to go through the line. A good line fit has about the same number of data points above and below the line. Then we write an equation. You get 2 points from that line, not your data. You get 2 points from that line. You find your slope, find your B. Write your equation in slope-intercept form and use that equation to make predictions by plugging in x or y values and solving for the other. When you are using the linear equation to predict values that are outside of the range of data, you're finding the linear extrapolation. And when you use it to find or make predictions of values that are inside the data range, you are finding linear interpolation. So I want you to circle extra, and that means outside. And I want you to circle this one, and this means inside. Those are just definitions you need to know. So if we plug in numbers and it is way outside of our range, that is the extrapolation, because it's outside the range. And if we plug in the x value and we get a y value that is inside the data range, then that is interpolation. Now let's look at example 2. The table shows the average cost of a jet boat in the years after 2000. Write and interpret an equation to represent the data. Then use the equation to predict the cost of a jet boat in 2005 and 2025. Step 1, make a scatter plot. Like I said, time will always be your independent variable. So the years since 2000 goes on my x-axis, and the cost in dollars goes in my y. As you can see, they're counting by twos on my x-axis, and then they're counting by 5,000 on my y-axis. Well, they count by ones because you can put a 1 here. 1, 2, 3. So they count by ones on the x-axis and 5,000 on the y. So they made their scatter plot. Once they made their scatter plot, they realized we have a positive correlation. I want you to circle that, or you may have to write it in because my points are increasing. Then you draw a line of fit. A line is drawn that follows the trend of the data point and passes close to the most of the points. I want you to write down that. So I want you to write down no points don't have to be on the line. It must follow the trend. So as you can see, barely any of my dots are going through my best fit line, but that does not mean that's not a best fit line. It's following the trend of my points. So that is the line I'm going to use to write my equation. So you need to find 2 points on the line. Now, no, I'm not talking about the points that you see that are around my line. You need to find 2 points on your line. So let's see what 2 points they use. So the 2 points they used were 5 and 25,108 and 10, 32,752. They labeled their points, plugged it into the slope formula to find the slope. Once they found the slope, they used the point slope form to write the equation in slope intercept form. Now this is what I can use to make predictions. The slope indicates that the cost of the jet boat increases about $1,528.80 per year. The y-intercept indicates that a jet boat costs about $17,464 in 2000. So since we're starting my data in 2000, that means 2000 is the initial year, meaning that this is when x equals 0 and 2000 represents x equals 0. So that's why they said that about my y-intercept. And again, I'm using this equation to make predictions. So they want me to make a prediction about the cost in 05. I'm going to make my x value 5 because again, we are doing 2005 minus 2000 because this is our initial. So x is 5. You plug in 5 for x and then you solve. So we can predict that the cost of a jet boat in 2005 was about $25,108. Now, this is a prediction, meaning this is not the actual accurate answer, being that we do not have an actual linear function. We just drew a best fit line. That line is not an accurate representation of my data. It is just a close relationship between my data, so I can use it to make predictions. So this is not saying that every jet boat was that price in 2005, but they should have been around that price. You can also get different equations because your best line fit depends on how you draw your line. So if you drew your line a little lower than mine, you may get 2 different points and get a different slope and a different y-intercept, but our values should be about the same. They should be in the same range. Then we do the same thing for the cost of 2025. 2025 minus 2005 is 20. I'm sorry, my initial year is 2000. So 2025 minus 2000 is 25. That's where that 25 came from. I plug it in for x and then I solve. So So you can predict that the cost of a jet boat in 2025 will be about $55,684. Now I want you to do the check. The data shows the amount of milk that a baby goat needs by its weight. Part A is telling you to use the data point 1020 and 5080, which are indicated in the line of fit, to write an equation of the line in slope-intercept form. And we know slope-intercept form is y equals mx plus b. So the best thing to do is first, you got to find your slope. Then I will put it in point slope form and then simplify that to slope intercept form. Then they want you to use the equation from part A to predict the amount of milk needed for a 17-pound goat and a 55-pound goat. So the equation you get, they gave you two x values, x equals 17, and they also gave you x equals 55. So you're going to plug those values in for x and solve for y so you can get your values. And these are the answers you should have gotten. So for part A, my equation is y equals 1.5x plus 5, or you have 3 over 2x plus 5. Now you plug in 17 for x, and you should have got that a 17-pound goat needs 30.5 ounces of milk, and for a 55-pound goat, they need 87.5 ounces of milk. And that is the end of this lesson. So there will be a worksheet that I want you to work on before you move on to the practice on McGraw-Hill. Again, there is an independent assignment that I want you to work on in class before you move on to McGraw-Hill. So once you finish this video, please collect the practice so you can get started. Hope this helps.